Based on circumstantial evidence, we previously concluded that entropy was a measure of disorder. But classical thermodynamics does not explain exactly how entropy is related to disorder, nor does it explain why spontaneous processes always increase the entropy. Answers to these questions are provided by Boltzmann's formula for entropy, which is also termed the statistical definition of entropy, to contrast it with the classical definition of entropy. This formula tells us that entropy is proportional to the log of W, the multiplicity of the system. By the multiplicity, we mean the number of microstates that is compatible with a system's macrostate. The macrostate is the state of the system as given by all its thermodynamic properties, while a microstate is a state in which the condition of each molecule or atom in the system is defined. In general, macrostates are observable, but microstates are not. We can view W as a measure of our lack of knowledge about a system. As W increases, our knowledge of a system decreases. Consider, for example, a set of 100 coins, each of which is either heads up or tails up. The macrostates are specified by the total number of heads and tails, whereas the microstates are specified by the condition of each individual coin. For the macrostate consisting of 100 heads and 0 tails, there is exactly one possible microstate, so our knowledge of the system is complete as we know the condition of each coin. At the opposite extreme, the macrostate that gives us the least knowledge about the system consists of 50 heads and 50 tails in any order, for which the number of possible microstates is exactly 100 octillion, 891 septillion, 344 sextillion, 545 quintillion, 564 quadrillion, 193 trillion, 334 billion, 812,497,256. Consequently, there are over 100 octillion times as many microstates with 50 heads and 50 tails as there are microstates with 100 heads and 0 tails. So the macrostate with equal numbers of heads and tails is far more probable than the macrostate with only heads. Another illustration of these ideas is provided by this bed. In this case, we'll define two possible macrostates, a neatly made bed and a messy bed. If you were to jump up and down on the neatly made bed, it would rapidly turn into a messy bed. But no matter how long you jumped up and down on the messy bed, it would almost never turn into a neatly made bed. The reason for this is that there are a lot more configurations of the blankets, sheets, and pillows that are compatible with the disordered high entropy state than configurations that are compatible with the ordered low entropy state. Here on Boltzmann's tombstone in Vienna is his famous equation in which he postulates a logarithmic relationship between entropy and multiplicity. Why did he invoke a logarithmic relationship instead of some other kind of relationship, such as a linear relationship? It's because he noticed that by invoking a logarithmic relationship, he ensured that calculations of entropy changes based on the statistical definition of entropy would always agree with such calculations based on the classical definition of entropy. So you could say he rigged the system to ensure that the classical and statistical thermodynamic entropy calculations would agree. In essence, Boltzmann's equation allows us to replace the classical statement of the second law of thermodynamics with the idea that the most likely future universe is the most probable one.